All right, integral e to the negative y cosine y dy. All right, remember Lipit, we have an exponential and a trig. I'm going to let you in on a secret. Exponential and trig are really tied. It doesn't matter which one you make u. But I'll go ahead and just do it the way we normally would. So I'll let u equal e to the negative y. And I will let dv be cosine y dy. Seems like maybe a good time to mention again, on this side, you are differentiating. Derivative of e to the negative y is e to the negative y times negative 1 dy. Really, we're doing a differential there. And the integral of cosine y dy is sine y. So integral u dv is equal to uv minus integral v du. We have integral e to the negative y cosine y dy is equal to e to the negative y sine y minus the integral of v du. Notice there is a minus here, so that is going to change minus integral v du to plus integral e to the negative y sine y dy. All right, so now I will put that integral in a red box, and that will become the red integral. And we will do integration by parts again. Let u equal e to the negative y. And let dv this time equals sine y dy. Then du is once again going to be negative e to the negative y dy. And v is going to be the integral of sine y dy, which is negative cosine y. All right, so the red integral works out to negative e to the negative y cosine y. And this time we have triple minus. We have the minus in the formula. We have a minus here and we have a minus here, so that's still going to be a minus. Minus integral e to the negative y cosine y dy. All right. And at this point, you might be scratching your head. I was literally just scratching my head just now. All right. Because it kind of seems like we're going around in circles, doesn't it? All right. So let's see where we are. Remember, this was the original problem. So now let's substitute what we have for the red integral. We have integral e to the negative y cosine y dy is equal to e to the negative y sine y Okay, now, whoops. Okay, so now I'm ready to substitute what I have for the red integral. So instead of writing this integral, I am going to write this. I'll write it in red, just in case that helps. So we have plus, I'm being super careful with my signs here, SIGN. And then minus integral e to the negative y cosine y dy. So on the one hand, it kind of looks like we're not getting anywhere. And I remember the very, very first time I saw a problem like this. When it was explained to me what to do next, I thought that somebody was trying to trick me. It didn't sound legit to me. So what do you have? You have integral equals term plus term minus integral. But notice these two integrals happen to be exactly the same. And I would even take it if, you know, one of them was a multiple of the other, because here's what I'm going to do. Let me get rid of those lines so nobody thinks they are fractions. I am going to add this mystery integral to both sides. And look what I end up with. On the left-hand side, I get 2 times that mystery integral equals term. Okay, and now I'll drop this extra plus sign and just write minus e to the negative y cosine y. And I was trying to find the value of that integral. Well, I have 2 times that integral is equal to this minus this. So now all we have to do is divide both sides by 2. And we get integral e to the negative y cosine y. And now I'll do some pretty factoring, is equal to e to the negative y over 2 times sine y minus cosine y. And of course, no points if you don't remember, plus c. Just kidding. Yeah, I remember the first time I saw this, I thought, but it feels like you never actually solved that integral. But really you have, right? Think of it as like algebra with integrals. All right, so there you have it. And by the way, my tabular integration trick is going to work on these two. So let's talk about that next. Okay, tabular integration is great whenever you have to use integration by parts more than once. So I love it for this integral. And it turns out it even works for this integral. I think these are the 2 examples that I have. And then this example here actually has nothing to do with tabular integration. That's just an additional example that's kind of fancy. All right, so let's go to back to the tablet one last time. And once we get through these 3 examples, we will be done with 8.2. All right, here we go. All right, so this integral would be super tedious if you had to just use, you know, integration by parts the same as we were doing a minute ago. So here's how tabular integration works. You pick your u and your dv. And we have a polynomial and an exponential. So the polynomial gets to be u. All right. Differentiate u, ideally, until it becomes 0. So that's going to be 4p to the 3rd, and then 12p squared, and then 24p, and then 24, and then 0. And then you're going to integrate e to the negative p the same number of times. And I guess this is technically a baby u substitution. Remember, I am integrating on the dv side. So it's going to be e to the negative p, and by baby u substitution divided by -1. And then just do the same thing over and over. All that's going to happen, right, is it's going to just alternate between positive and negative. And then, this is so gimmicky, the way that you get your answer is you match the first thing on the U list with the second thing on the DV list, and the second thing on the U list with the third thing on the DV list, et cetera, et cetera, et cetera. with alternating signs starting with plus. All right, so it turns out that the value of integral p to the fourth e to the negative p is okay, don't miss the negatives that are there. So this is going to be negative p to the fourth e to the negative p minus 4p to the third e to the negative p minus again, I guess these are all going to be minus, 12p squared e to the negative p. Not even going to get it all on one line, minus 24p e to the negative p minus 24 e to the negative p plus c. That's it. Isn't that simple? And if you wanted to, I can't resist. I'm going to write this as negative e to the negative p times p to the fourth plus 4p to the third plus 12p squared plus 24p plus 24 plus c. You absolutely do not have to do that, okay? I just think it looks a little nicer. Okay, so that's one version of tabular integration. Here's another version. So remember we just did an example like this. This is the one that I thought was, I was being tricked the first time I saw it. In this case, nothing ever becomes zero when you differentiate. So there is a slightly different version of tabular integration for those. I actually didn't learn this myself until quite some time after I learned the other version. So I would just suffer through these and do them the long way. What you do with these, so I'll make this e to the negative x, I'll make this sine 2x. When I differentiate e to the negative x, I get negative e to the negative x. By baby u substitution, the integral of sine 2x is negative cosine 2x times 1/2. So negative 1/2 cosine 2x. And then we do it one more time. The derivative of negative e to the negative x is e to the negative x. And the integral of negative 1/2 cosine 2x is negative 1/2 times the integral of cosine 2x, which is negative 1/2 times 1/2 sine 2x. So that's going to be negative 1/4 sine 2x. And I'm going to stop right here because in this version of tabular integration, you stop when you notice that you have a row where the functions are exactly the same as the ones you started with, except maybe with a different coefficient in front. All right. And I'm pretty confident that 99.9% of the time, you're only going to need to differentiate and integrate twice. In other words, your UDV table will have 3 rows. And then you start doing it the same as we did it on the other one. Okay, but the catch is that then you have to add, let me do this in red, you have to add the integral of that product. So let me show you what that looks like. We have integral e to the negative x sine 2x dx is equal to negative 1/2 e to the negative x cosine 2x. I better be careful here. We have triple minus, right? 1, 2, 3. So that's going to be minus 1/4 e to the negative x sine 2x And then it's, okay, this is by default a plus, but we do have a minus right there. So that's going to be minus 1/4 the integral of e to the negative x sine 2x. Okay, so it kind of reminds me of that other problem. We have integral is equal to term plus term and then minus 1/4 that same integral. So all we have to do is add 1/4 that integral to both sides. I'm going to squeeze this in at the bottom, and then I think I'll have to go on to the next screen. Okay. What is 1 plus 1/4? It's 5/4, right? So on the left side, we have 5/4 integral e to the negative x sine 2x dx is equal to negative 1/2 e to the negative x cosine 2x minus 1/4 e to the negative x sine 2x. Actually, you know what I think I'm going to do? Instead of going on to the next screen, I think you'll follow me better if I just do it up here. Okay. So what we need to do now is multiply both sides by 4/5. So I'm going to squeeze that in down here. All right, and then I'm going to write it up top. So what we have is the integral e to the negative x sine 2x is equal to 4/5 times negative 1/2 is negative 2/5. And that's e to the negative x cosine 2x. And then 4/5 times negative 1/4 is negative 1/5. So that's minus 1/5 e to the negative x sine 2x. And of course, no points if you don't remember the plus c. Just kidding. So hopefully that trick makes these problems a little less painful. All right, I'd say maybe about half as painful. Okay, I have one more example to show you. This one has nothing to do with tabular integration, but I have never had the opportunity to show you what I call a tricky substitution. This is a great example of a tricky substitution. All right, so it's integral e to the power square root of 3s plus 9. So if you think about doing this, you know, some other way, I don't really know how you would do it. I don't think I know how. Well, I shouldn't say that. I don't know any way other than the one I'm about to show you to do even e to the square root of x. All right, it's not a substitution. It's not, to me, an obvious integration by parts. So check this out. Back to regular old substitution to begin with. And I'm going to do this as a z substitution because I'm thinking ahead and my brain doesn't really function. If I have to use integration by parts, I sort of have to use u for that. Right? I mean, if I absolutely had to use some other letter, I guess I could. But if I suspect I'm going to be using integration by parts, I try to reserve u and v for integration by parts. So let's do this as a z substitution. I'm going to let z equal the square root of 3s plus 9, which of course is 3s plus 9 to the power 1/2, which then will make dz 1/2 times 3s plus 9 to the power negative 1/2 times the derivative of 3s plus 9. Now you see why I didn't write the 1. And don't forget your ds. Okay. Okay, well, great, Mitchell. What does that do? Well, let me show you. So what I'm going to do now is I am going to divide both sides. And I want to be transparent with you. This is not a problem. A lot of these problems I can just pick up and do. I tried this one out first. I wanted to make sure I remembered how it works. So please don't think that every single calculus problem is something that I can do in my sleep. Okay. So on the right side, of course, everything cancels out and we're just left with ds. On the left side, we are dividing by 3/2, which is the same thing as multiplying by 2/3. We are dividing by 3s plus 9 to the negative 1/2, which is the same thing as multiplying by 3s plus 9. Oops, let me try that again. To the 1/2, isn't it? And then I have this dz here. Okay, well, this kind of looks like a mess when you first look at it because I've got my s's and my z's all mixed together. But guess what? Does this 3s plus 9 to the power 1/2 look familiar? Do you know what that is in terms of z? I think you do. It is exactly just z. So guess what? I can write that as 2/3 z dz. ds is going to get replaced with 2/3 z dz. And then here's what we're going to have. We're going to have e to the square root of 3s plus 9, which is going to become e to the u. And ds, I'm sorry, e to the z. And ds is going to get replaced with 2/3 z dz. And now maybe you understand why this problem is in the integration by parts section, because we have to now integrate that by parts. So let's do it. This is an easy integration by parts. Let u equal z and let dv equal e to the z dz. Then du is just dz and v is just e to the z. All right, so I better be careful here. I got this 2/3. 2/3 integral z e to the z dz is going to be 2/3 uv, which is z e to the z, minus integral v du, which is just integral e to the z dz. So that's going to be 2/3 z e to the z minus e to the z. But this isn't about z. This is about s. All right, so final answer. Shall I write the final answer up here? I think we're done with this part. Okay. Two-thirds times the square root of 3s plus 9 times e to the square root of 3s plus 9 minus e to the power square root of 3s plus 9 plus c. All right. And that's what we call, or that's what I call a tricky substitution. Those float up every so often. They're kind of fun, but they do take some practice. And that's what I have to show you for integration by parts. We'll see you next time.